Hello all, so let's discuss a really unique and famous problem called climbing stairs, or it's also a staircase problem. So we know this problem a bit already because we know that it's a really famous problem. So let's try to solve it. That the question says that we are given a staircase. Let's say we have n staircase in general. Here I have just drawn 5. But what the question says is that given a staircase, we have to find all possible paths or all possible distinct ways you can climb to the top. But the only condition is like you can climb either one step or two steps at a time. Okay, so by doing this, we have to find all possible. So, for example, we have just two stairs, then it's easy. We can do it in our mind that we can take one step twice, or we can just take two steps at once and we are reached at the top, right? So there are two possible ways. That's why output is 2. But in case of 3 stairs, then we have 3 possibilities, one each, or you can take one step and then two steps, or the other way around, two steps and then one step. So in total, we have 3 unique ways, right? The distinct ways. That's what we have to calculate. And let's see now a bit intuitive way. Like we know that this can be solved using a recursion because we can do in our mind for 1, 2, or 3 staircase, but as the number increases, it's not possible, right? But why I said recursion, right? And after, as I already always said, first try the greedy one, and the greedy one here won't work because we have to go with all possible combinations or all possible permutations, right? And that is a bit tedious and it's not possible as an algorithm. So one way is to go exhaustive, right? So if we go exhaustive, that what's that exhaustive way? Exhaustive way is that at every step we will find, let's say we are doing for 3. Okay, so let's say at every step we have two possibilities. So we are right now we are on the ground. So in order to climb to 3, let's say we have just 3 stairs, then every step we have two possibilities. Either we can take one step or either we can take two steps. So if we take one step, then we are left with still two steps, and if we take two steps, then we are still left with one step to climb. Now again we have two possibilities, like one step and two steps. So if I take one step again, then again I have to climb one step, and if I take two steps, I'm done, right? So this is one of the valid path, right? So when we hit 0, then this will be our base case, or one of the base case, that if when we are done, we will say that this is one unique path, and this will output 1, that okay, this is my unique path. Now let's continue from this one, that again we have two possibilities. Either we can take one step or we can take two steps, and we know that if we take two steps, it's not possible, right? So here we will return 0, that this is not possible. So when we reach, like, fundamentally we are going to -1 if we take two steps, right? If we subtract 2 from, right, 1 minus 2 is -1. So this is also one of the base case. So but when this will happen, we will say it's a invalid path. Okay, so this path is not valid. So since we are calculating total possible ways, so this will return 0. Okay, so 0 ways. Here we can say we have one unique way. Here we have 0 way. But again, going down here, we are getting, if we take 1, then we know that for climbing to 3, we can take one step, right, thrice. And this is a valid path. So we will return 1. So at the end, we have to return all the unique paths. So what we will return to the parent is the addition of both of them, right? So for example, if this is also one of the valid path, then we will have one here as well. So there will be two unique paths, right? So addition is what we have to, but here the addition is 1, right? Similarly, we should go again this side, that over here we have two possibilities. Either we can take one step or we can take two steps. And again, two steps will be negative, right? So this is not a valid path. This will be -1. So it's not a valid path. So if you will see, and here we will 0. So if you will see, we again spotted a repeated sub problem. So this and this is the same, right? If we grow the tree down from the one, then it's a repeated sub problem, right? So if we have calculated already here, then we will just use directly that value here, and that leads to DP. So firstly, we started with the exhaustive way, right? And this exhaustive solution will take how much time complexity it will be? It will be 2 power n, where n is number of steps. So why 2? Because every time we have two possibilities, either one step or two steps. Similarly, if someone says someone is really tall and can take 3 steps, then we have 3 possibilities. So the solution remains the same, right? So we have every time 3 possibilities. So 2 power n, which is exponential time complexity, and space, it will be O of n, but this will be giving us time limit exceeded. So let's code it out first quickly using recursion. So this is a really brute force way of doing it, and we will see that it's eventually get it towards Fibonacci sequence. If you don't know that sequence, it's fine, it's the school mathematics, but let's focus on writing it, and I'll try to be quick as possible. So I'll write, this is a DFS, or so let me call that DFS, and let's handle the base case as well, that if we are given 0, then return 0, right? I mean, it's not given in the constraint, but it's good to write. Yeah, it's always greater than or equals to 1, so doesn't matter if we write this or not, but let's put it. And at the end, what we have to do is I will write this function self.dfs on this n, and let's now write the function. So it's a DFS, and n, it's our int, and it also returns the int. Okay, so in recursion, always we follow the same template. First is the base case and the logic. First we will write the logic, and then comes to the base case, and we have seen our base case already. So in logic, every time we have two possibilities. So first possibility is just take one step. So if we just take one step, let's call it case one step. I mean, there can be a better way to name it, but let's call this. And what we have to do, if we take one step, then we are still left with n minus 1 steps to climb if we take one step. And case 2, when we take 2 steps, let's call it case 2 steps, then we are still left with n minus 2 steps to climb. And what we have to return, as I said, we have to return the summation. So I'll just copy paste. So we have to return case 1 plus case 2. Oops, case 1 and case 2, and we have to add them. But what about our base case, when we should stop the recursion? So of course we have seen that when our n is 0, so when it's a valid path, right? This is the valid path. This is also our base case, right? This we have seen here. This is also our base case. And when it's negative, that's also our base case. Then we have to stop. So when n is 0, but since it's our valid path, we have to return 1. And when n is negative, right, then we have to return 0, because it's not a valid path, so don't count it. So let's try to run it and see if there any mistake. No. So it will work for small number of n's, but for larger values of n, it will give us time limit exceeded, right? So you can see it's still judging, and it will eventually give us time limit exceeded. And that's why we have to see that. So it's not incorrect, it will work for small values of n, but as you can see here, when my n goes to 38, then it's too much, right? It's 2 power 38, it's too much, right? Too much computation. So as we have spotted already the repeated subproblems, so let's go to that. So now I will follow the template of recursion, then memoization. Firstly, in the coin chain, we just jumped to tabulation because it was the very first problem that we did, coin change one on dynamic programming. So it was easy to explain, because recursion is a bit overwhelming at first glance. But now what I'll do is I'll directly go to memoization, and we will go to tabulation, but just I am changing my flow. Okay. So firstly, let's go to the memoization part. And here time and space both will be O of n, and we will see why. And we know from our coin change problem that why memoization takes O of n only time, because we store it in the dictionary. So we will have, let me copy the entire thing and just modify in there. It's better, I guess, saving some time. Okay, so let's copy. Just we have to modify a few lines and we are done. Okay, so firstly what we need is a dictionary in which we will store our already computed. So why this dictionary is needed? Because as I said, we already spotted the repeated subproblem, right? So whenever we calculate for this one, right, we will just use it here. Okay, so that calculation answer we are getting is 1, right? So that 1 is being stored in that dictionary. Okay, so nothing much, it's just this thing. Okay, so and what we have to do is, in the base case, we have to enter that if we have already calculated that subproblem. So if my n is already in the memo, then we will directly return. So this will save us the recursive call. So just get that value, whatever is being saved for that particular n, and give it. And here, every time we have to store. So self dot memo of n, and what should be the answer? We know the answer should be addition of 2, and at the end we are returning self dot, I mean we can return the addition as well, self dot memo of n. Okay, so let's comment this out and let's run this and now see if it's working. Yes, it's working. And now no time limit exceeded, and you will see the time is also O of n. Why? Because we are just visiting every node once only. So we are not, this is being say, if we have calculated once this subproblem, here we are saving that recursive call. So we are not growing that tree beyond. So every time we are saving recursive calls, and that's why we are just visiting every steps. So every time we are decreasing from the steps 3, then 2, then 1, based on whatever decision we take, right? But we are just calculating everything just once. Okay, same as coin change, nothing, same pattern as coin change. Now let's go to the DP with tabulation. Okay, so let me write. So this will also take O of n time, O of n space. Sorry, we will see that. So DP with tabulation, and let's copy this thing. So now for this, I'll again go to here and let's utilize this. So we know this is, let me write, this is 1 step, 2 steps, 3rd, 4th, and 5th. Okay, so how to visualize DP? Let's see that. So this is my DP array, and we know that for climbing 1 step there is always just one way. Okay, but for climbing 2 steps, given our rules that one can climb either 1 step at a time or take 2 steps, so there are 2 possible ways, correct? So this is always fixed, no matter the length of the staircase. This is always fixed, at 1 and 2 always fixed. But now for 3, we know that what should be the answer. Logically the answer should be 3. And how 3? If we calculate in mind 2 1 or 1 2, right? These are the 3 possible ways. But how can we calculate this here? How can we build that intuition here? So in order to build that intuition, let me explain that. For example, let's say we have to just we have 3 steps. Okay, I'm calculating for n equals to 3, just showing you for n equals to 3, ignore the rest of the steps beyond 3. So, and this is always fixed. Now in order to climb to stair 3, let's say I am at stair 2. In order to climb at stair stair 3, what we have to do, there is one possible way is, if we are at 2, we can just directly go here. Okay, so all possible ways to reach 2 plus one step will lead me here. But you can also argue that, for what about if I am at 1? So all possible ways to reach at staircase 1 and then take 2 steps, right? So in simple words, what I mean is that if I have to climb to staircase 3, then one way is all possible ways to climb at staircase 2, which is 2, right? And then just plus 1 to it, or not like plus 1, it's at one step, so it's one possible path. Okay, so all possible paths until 2, and just one more step will lead us to 3. But you can also argue that since we are allowed to climb 2 steps at a time, we can also climb from here, right? All possible ways until step 1 and just jump directly here, right? So that is also one of the unique path, right? So at the end, to climb at 3, so what I can say is, to climb at 3, all there are two possible ways, that all possible paths up to 2, to climb up to 2. Okay, let me write up to 2 plus all possible paths to climb up to 1, right? Because after, if we are reached either at second step or first step, it's just one more step that we have to take. I mean if we are at 1, we have to take also one more step, but this step will be of size 2, but at the end we have to take one more step. Here as well we have to take just one more step, but here the step size will be just 1. So if we can do this, if we can get this and this, we can easily get the next number. So simply it's the addition of previous two, if you will notice. And this is similar to Fibonacci sequence or Fibonacci sequence. I don't know what to pronounce correctly, but the idea is the next number is the summation of previous two numbers, right? Similarly, if we want to calculate 4, then we can say it will be 3 plus 2, 5. And if we calculate for 5, it will be 8. So again, just to repeat that, if I have to climb to 4, what I have to do is, one possible way is all possible ways until step 3 and plus 1, or all possible ways until step 2 and just one step of size 2. Okay, so at the end we just have to sum previous two and we will get it. So the same concept we will utilize here, and let me write that. So firstly let me make the DP array. So the DP array will be 0 and how much? 4 in range until n. Okay, so it will be having, we will have n zeros at the end, and always we know this, that first will be 1 and second will be 2. This is always fixed irrespective of the size. So we will start filling from third index, or I can say second index. Okay, so 0 and 1th index are fixed, so we'll start from 2 until n, and always my next is summation of previous two. It's like I minus 1 and dp of I minus 2, and at the end we have to return the last value in the array, and we are done. Let's comment out this thing and let's run this and let's see. Okay, it's working. And okay, there is some problem. DP of 1 is 0. Okay, we missed the base case, that if my n is 1, then simply return 1. This we already know. Perfect, it should work now. Okay, now let's optimize this. So as I said, if you will notice, we just need two variables. Okay, we don't need this entire array because it's taking over extra space often, right? And I hope the time and space are clear, that we are just getting through entire array once, not entire array, but from 2 to n, but at the end n minus 2, but constant doesn't matter, so it's O of n at the end. And space is also O of n because we are storing in the size of n. But can we optimize it further? And yes, we can do. Let's write that space optimized. Okay, let's comment space optimized to O of 1, and we will see how, because we can see we did the same thing for coin change, right? That if it's possible, we can still do it. So we are doing it. Space optimized. And here simply what we need, again, we will need that base case, that if it's 1, then simply return 1. We just have one possible way. Now what we have to do is, let's take current step equals to 1 and next step equals to 2. What I'm doing is, let me explain it here, that this 1 and 2, which we already know, right? I'm just storing it that into two variables named current. Let me draw it again. For let's say n equals to 3. So what I'm doing is, this is my one variable which I'm calling it current, and this is next. So in order to calculate this, what we have to do, we have to sum this two. So it will be 3. Now if I have to calculate this, what I have to do, I have to just sum this. So what I have to do now, we have to make just shift this current and next. Now this will be current, and we can calculate our next value. So this is how it goes. So I'll just simply write it here, that for two things it's done. So again here we will start from 3 until n, and what we will do is, we'll see, we have to take until n or n plus 1. Okay, so firstly what I have to do, firstly I'll just store my next step into temp. So what I'm doing is, whatever my this value is, we started with this as our next, so I'm storing this in temp. Okay, because why I'm storing it in temp, because I have to make this as next now, just to avoid this overwriting, I am storing it. Okay, so my next step is now temp, and now my next step will be whatever was the current step plus the next step. Now the next step is overwritten, that's why I need to store this to temp, and now just simply make my current step to that temp. Okay, and at the end return our last value, which is next step, and let's see if there is some mistake. Yeah, there is a mistake. And what's the mistake? The mistake is, we are going from 3 to n minus 1, and we know that because n is not counted, right? Here we started from, so for example, here we started at dp0 as 1, and that's why we went from 2 to n. But here we are just starting as two variables, right? We are starting from 1 and 2. So for because of that reason, what we have to do is, we have to go until n plus 1, and it will work. I hope it's clear. And now we are just using constant space. If you want to check, we can check as well. Yeah, you can see. So that was the really simple thing about staircase problem. So we started with recursion and went until the DP tabulation, the most optimized form. I hope things are clear. We are following the same template as we did for coin change and other dynamic programming problem. So stay tuned and keep learning. Thank you.